Welcome to Maths with Bob. Today we're looking at solving trig equations by a technique called the auxiliary angle method. It goes by lots of different other names, sometimes a subsidiary angle method. There are other names as well for it. But basically it revolves around the fact that any function of the form a sin x plus b cos x can be combined into a joint expression, using the sum and difference of angles. You can see here it can be written as r sine plus or minus alpha, or r cos plus or minus alpha. This alpha being the auxiliary angle, and usually we get the acute angle, and it's actually, well, we can actually derive this, that it's actually alpha is inverse tan b on a, and the r at the front expression is the square root of a squared plus b squared, and we'll actually go through and look at that in a minute. But how can this occur? I just wanted to show you. Okay, oops, that's the wrong GeoGebra. We should. Okay, if you have a look here, this is actually GeoGebra, and I've just got a function. You can see there it's actually a sin x plus b cos x. That red line is actually c equals 2. That's the actual value we're going to try and solve it, and you can see that what we would be trying to find is those points of intersection with this particular graph and that red line, or the blue, and where the blue line actually, well, the blue graph actually cuts the red line. Okay, now as you can see here, this is actually the combinations, and you can see here they are just forming one wave, and that's what this is the idea, that we combine them into one wave, and then we try and solve where they actually equal this red line here. Okay. All right. Well, okay, we're asked to solve 2 sin x plus 3 cos x equals 2. And we've got some options here. Okay, okay, so let's have a look. Which one of these would we use? Well, first up is, okay, will we use sin x minus alpha? No, it doesn't fit the sin x minus alpha expansion. Okay, it does fit this one, so we could use this one, yes. Okay, we could use that one. And what other one could we use? Well, remember the cos, we could also use this one. Okay. Now sometimes you are given a direction as to which one to use, and that makes it a bit easier. But if you actually have to choose, you obviously choose the one which fits the expansion the best. So we're going to start with, let's start with what? R. Okay. Now we're going to use sine. Just use the sine one to start with. So x plus alpha. Okay. So this is the first one we're going to use. Now, okay, so the first thing I always do is just rewrite out the expansion. So it's equal to, this will be equal to what? R sine. Let's have a look. I'll put the brackets, put the r right at the front. X cos alpha. Now plus, okay, we obviously swap around. Cos x, and then sine of alpha. Okay. So fitting this to this expression, you can see here that what? R cos alpha, okay, and R sine alpha. Let's have a look. What are they equal to? Well, we can see here, well, what, the 2 is in front of the sin x, okay? So what's in front of the sin x? Okay, so it's basically these, very, yeah, it's r cos alpha. Yes, so that's equal to 2. Okay, so let's actually type that in. Okay, so that's equal to, this should be equal to 2. Okay, let's have a look at the other one. Okay, we have 3. Okay, we can see the 3 here. It's in front of the cos x. Okay, cos x, what's in front of the cos x? Well, that's this sine and the r as well, you can see here. So we can see that r sine x must equal 3, hopefully. Okay, now once we've got this, we can obviously basically get the alpha and the r from this expression. So how would we do it? Well, if we had, just have a quick look to get the alpha. Okay, we'd always just go r sine alpha over r cos alpha, and we just say that's equal to what, 3 on 2. Now we can see here the r's would cancel, giving us the tan of alpha is equal to 3 on 2, and this would obviously give us that alpha. Okay, alpha would be equal to what? Tan to the minus 1 of 3 on 2. Okay, I'm just going to leave it as inverse tan 3 on 2 at the moment. Okay, so that's our auxiliary angle we're going to put into this expression in a little while. How about the r? Okay, so let's actually just have a quick look how we get the r. I'm just going to try and get the r. Okay, so let's just get a little bit careful with this rubber. Okay, now how are we going to get the r? Well, if we square both sides, we're going to get what? R squared cos squared alpha plus, and add them, r squared sine squared alpha. That's equal to 2 squared plus 3 squared. You can see here we have an r squared outside of a sine squared alpha plus a cos squared alpha. Famous identity there. Is equal to, what's that, 9 and 4, 13. So hopefully we can see that taking r as positive, should equal the square root of 13. Okay, so what we do now is we rewrite this expression, I guess you could say, as what? Root 13 becomes the r, the sine, now x, I'll just write it as the inverse tan of 3 on 2. Just keep it like this at the moment. Okay, so you can see here, another bracket. Okay, so we've now compacted 2 sine x plus 3 cos x into root 3 sine x plus this angle inverse tan 3 on 2. And that's going to equal 2. Okay, so our next step is to rewrite this. Okay. Well, okay, we are now just rewritten the expression root 13, sorry, sine x plus inverse tan 3 on 2 equals 2. Now, what do we do from here? Well, we divide both sides by root 13, so we have sine of x plus inverse tan of 3 on 2, okay, is equal to 2 on root 13. Okay, we have sine of x plus inverse tan 3 on 2 equals 2 on root 13. Then we just take the sine of both sides, or I should say the inverse sine of both sides, and we have x plus inverse tan of 3 on 2 is equal to sine to minus 1 of 2 on root 13. Okay. Now, we can see here, this is, I'm going to write the general solution. So that is some angle inverse sine 2 on root 13. Okay, so let's actually write down what would that equal. Remember, we had an n pi, then we had a plus, minus 1 to the n, and then we had this angle, which is in this case inverse sine of 2 on root 13. Okay, so we then move the the tan across, so we end up getting what? Solution equals x equals n pi plus minus 1 to the n, sine to the minus 1 of 2 on root 13, and then minus this angle tan to the minus 1 of 3 on 2. Okay, so we're going to now put in some values of n just to try and get some of these solutions, just to see. Okay, we're now going to try the cosine expansion, if you like, for this particular result. Earlier we actually tried the sine one because the sine one naturally fitted the pattern here. This is, if you have a quick look, this is the one we used before, the sine expansion. That fitted the pattern nicely. But you can see also, we could also use this cosine expansion, which we're going to be using, just to show that the answers are the same. Okay, so it doesn't actually matter which one you select. Obviously, you're going to select one which fits the pattern best. Okay, so let's move this away and have a quick look at. This is the snapshot from wind plot. Okay, we can see what we're actually after is we're going to be after these x values. You can see the coordinates of these points. I'll just try to make it a bit bigger. But basically, we are going to be looking at where that particular graph, 2 sine x plus 3 cos x, which is drawn here in blue, crosses the line y equals 2, that's the green, and we have these little red, if you like, triangles around the actual points of intersection. So these are the values which we're actually after. And you can see down here in the corner, interestingly enough, I've actually drawn the two graphs on top of each other. You can see here I've drawn y equals 2 sine x plus 3 cos x, and you can see here the black one, which you can't actually see, which is superimposed on the other one, is the, if you like, the subsidiary angle compaction of that to root 13 cos x minus a10, which is inverse tan 2 on 3. Okay, so we're going to be looking at that shortly. Okay, so what do we do? Well, first of all, what I normally do is just rewrite the expansion for cos x minus alpha out, and then equate the r cos alpha to 3 and r sine alpha to 2. Find r, get the angle alpha, and you can see here, and then put back into, okay, it's the square root of 13 cos x minus inverse tan 2 on 3. And as you could see before, in GeoGebra, you write that as a-tan, or I think that's actually short for arctan in the old days. It used to be arctan x instead of inverse tan x. Okay, let's have a look at this solution. Okay, what we do, obviously you can see here, we rewrite it as a compact form. Root 13 cos x minus a10 2 on 3 equals 2. Divide by root 13, and you end up getting that result there. Then you obviously take the inverse cosine, and using our general solutions, you might remember that it's actually every 2n pi plus or minus, so we need to go backwards and forwards by that angle alpha, in this case, which is inverse cos of 2 on root 13. If you have a good look at some of the solutions, I've actually just substituted in some numbers in just to have a look at some of the solutions. And if you compare that, I'll just bring across our, let's see if I can just make this a bit bigger. Okay, just have a quick look. Okay, here we are. Okay, so we have minus, and notice there the x values of these solutions. Just have a quick look. 1.57, okay, which is slightly out of the frame. I'll just move it in 1.57. You can see minus 0.39, 5.89, and 7.2. So you can actually see some of these solutions here. Obviously, there's an infinite number of solutions, as you can imagine. These are, well, if you like, what's called the general solutions, and that works for any integer value n. Now, I'm also going to be looking at showing this, or proving this little particular trig equation, or showing the solutions via what's called the t-results, okay, which we'll be looking at in the next video. But thank you for watching. Bye for now.